Here we have module 8B. We're looking at isentropic efficiency and do some examples for you on the use of isentropic efficiency. Comparing to ideal behavior, we have an ideal model for pumps, compressors, turbines, and nozzles. The work ideal is for reversible adiabatic operation. We'll call that work ideal. If it's reversible, recall that reversible processes, the entropy generated is 0. And for adiabatic operation, there's no heat coming in or out to carry entropy with it. So if it's a steady state operation, it's a flowing process, then the entropy in will be equal to the entropy out. So let's look at this. Suppose we have these steady flow processes. Here we have a turbine, a compressor, and a pump. All of these processes have the entropy balance shown below. The entropy generated is the out minus the in. So this is mass flow times S out minus mass flow times S in plus Q dot out, assuming they're hotter than the environment around them, and so heat would be flowing out, but we're going to assume they're adiabatic, so the Q goes to 0. Actually, that should be Q over T goes to 0, and the entropy generated goes to 0. So S out equals S in. We call those isentropic processes. And an isentropic process is our ideal situation. The isentropic efficiency compares the actual process to the ideal or isentropic process. So for a turbine, we have the definition of isentropic efficiency is the work actual divided by the work ideal, because we always get less work than we would ideally, and that number will be from 0 to 1 or 0 to 100%, and the efficiency will be a percentage of the ideal work that we'll get. In a compressor, we define it upside down, let's say, so the efficiency of the compressor is the ideal work divided by the actual work. In this case, the ideal work that we're putting in would be the minimum, and the actual work is always more, so we call that the efficiency, isentropic efficiency of the compressor. Also, we define that as the isentropic efficiency of a pump. Work where we're putting work in, we always have to do more, so for this to be an efficiency from 0 to 100%, the ideal work goes on top. Let's take an example. Air is expanded from 5 bar and 500 K to 1 bar in an adiabatic turbine having an efficiency of 85%. How much work is done per kilogram of air? So what we'll do is we'll calculate the ideal work that would have been done had this process operated reversibly. So for the ideal work, we'll let S2 equal to S1. So S generated is 0, and again it's adiabatic. So T2 ideal we calculate from our equation we developed earlier for isentropic processes for ideal gases at constant CP. And we have, plugging the numbers in, we wind up with 500 as it expands and work is taken out, drops down to 316 K. So the ideal work would be H1 per mass would be H1 minus H2, and that would be CP delta T, where T2 out is T2 ideal. So we calculate this would be 186 kilojoules per kilogram. That's the work we could get, but that is the best, the most we could possibly get. The actual work is less than this. So we know the efficiency is 85%, so what we do, multiply our ideal work times 85%, and we get actual work, 158 kilojoules per kilogram. Clipping through this pretty fast, so you should slow down and calculate these things as you go. Make sure you understand them as you go. What's the actual outlet temperature now? So we know the actual work now, 158. And that's equal to the delta H actual. So that would be CP times T1 minus T2. And we calculate the real temperature leaving that turbine would be, supposing that it is adiabatic, would be 344 K, which is higher than the ideal work. Now what happened? What caused it to be higher? basically was dissipation. It was friction of the gas against itself, against the blades of the turbine, because it was irreversible. Since it was adiabatic, the work or the dissipation couldn't get out, so it winds up in the gas leaving, and the temperature comes out higher than it otherwise would. Friction and dissipation heats the gas, and we have the air coming out a little hotter than it would had we had an ideal turbine where we could extract more work. Now I like to calculate the entropy generated for this process. And we know the outlet state now. We know the outlet temperature. Again, we'll assume the outlet pressure is the same. In fact, that's how the efficiency is defined, between the same two pressures, inlet and outlet pressures. So the S generated is, we'll plug in the numbers for the actual outlet entropy and the actual outlet temperature. And we'll calculate the entropy generated as plus 0.0837 kilojoules per kilogram. Had this been reversible, if we'd have put 316 here for the temperature, then we would have gotten 0 for the entropy generated, of course, because that was the reversible and adiabatic case. Here we actually have 0.0837. Looks like a small number. To really compare it to the work you need to get the irreversibility, multiply it times the temperature and you would. Now let's consider a refrigeration compressor. We're compressing refrigerant 134 in a steady flow compressor at 4 degrees C, from a saturated vapor at 4 degrees C to 10 bar with an 85% efficiency. How much work is required? Well, what I do in this process is I take my states, my properties, and my processes, and I have really two processes going from either 1 to state 2 ideal, the inlet state, to the ideal outlet state, or I'll put another place in my chart for the actual outlet state. And again, we're going from whatever the inlet pressure is for a saturated vapor at 4 degrees to the outlet pressure of 10 bars. And by definition of the isentropic efficiency, that's the same outlet pressure for the ideal state or the actual real state. We notice that in the case where it's ideal from 1 to state 2, the entropy is constant because we're treating it as reversible and adiabatic, so delta S equals 0. So notice you have two properties about state 1. You have the temperature and you have the quality, 100%. So you can calculate S. Knowing that S, you can get the S at state 2. That, along with the pressure, allows you to find the data for state 2. So we can calculate enthalpies at both state 1 and state 2. The isentropic efficiency of 85% is a link between state 2 ideal and state 2 actual, and that allows us to find two properties about state 2. So we'll be able to calculate the entropy later and determine the entropy generated here as well. So the entropy balance then, if you plug in the numbers, you should get numbers similar to this. Depending on the book that you use, what tables you pick up, you should get fairly similar numbers. And the entropy in is the entropy out. H2 is found. H2 ideal we find is a function of the entropy out ideal and the outlet pressure. By interpolation, we get H2 is ideal is 272. Calculate the work per mass. That's the outlet enthalpy minus the inlet enthalpy, be the work. Simple energy balance would be 22.5 kilojoules per kilogram. Now, before you move on, let me ask you, is the work that's done actually more or less? Here we're doing work, so the ideal work is 22.5. When you're doing work, the ideal work is always the lowest. We always have to do more work, so it's going to be greater. To find that work, I'll divide by the efficiency. Actual work is more, so dividing by that efficiency is a decimal. 22.5 divided by 0.85, and we had to do about 4 units of work more than we would have had to had it been a reversible process. So the H2 actual, plugging that back into the energy balance, we can find the outlet enthalpy. It's 276. And from that, knowing what you know about properties, S2 is a function of the enthalpy and the pressure, and that comes out to 0.9296. Finding the entropy generated, we find that it's positive, as expected. S2 minus S1, always going to be positive. And using the same sort of interpolation that we did before, we'll find T2 actual is a function of P2 and H2, and it's 46.4, which is greater than it would have been had it been an ideal process. Again, the energy dissipated winds up in the gas leaving, in the fluid leaving the compressor in this case, and it raises the temperature leaving the compressor. So filling out all the information in the table, and again I'd encourage you to stop and do this. You'll get all these properties here. Notice that the entropy here is the same at 1 to 2 ideal, but slightly higher for state 2, the actual outlet state. If we put a thermocouple or a temperature sensor on this outlet state, we'd get 46.4, not the 42.8 predicted by the ideal compressor. Alright, let's look at another problem, and this one I want you to do for homework. Suppose steam is expanded in an adiabatic turbine from 10 bar 500 C to 1 bar, and suppose that the turbine efficiency is 80%. I want you to determine the ideal and the actual work, the outlet temperature, and the entropy generated. This is very similar to the problem we just did, except now you're using steam and you're drawing work out. So try this problem. When you do it, take a look at the Moliere chart. Moliere chart is extremely useful for solving steam turbine problems, and try to do it with just the data on the chart. Finish this problem with the tables, charts if needed, tables if needed, and indicate the ideal and real states on your Moliere chart, and you'll notice that the entropy is definitely increasing, and you can find the outlet temperature as well fairly quickly from that chart. So we've looked at the isentropic efficiency, and that's something that I use a lot. Compares the real work to the isentropic work. It's based on the same outlet pressure as it would be in the real case as it would be for the ideal case. So be able to do those calculations backward and forward. Be able to do it for compressors, for turbines, for pumps. Be able to do it for ideal gases. Be able to do it for using tables. And finally, this is the last homework for this segment, I guess, where we're talking about entropy. Next we'll go into cycle problems, where we're looking at stringing several pieces of equipment together. But for now, take a look at the steam turbine problem that I just indicated, and finish reading chapter 7 and work all the remaining problems, especially those with answers. Work as many problems as you can, especially those with answers through 7-164.